Hi there. Thanks very much for having us at the CIBSE Technical Symposium 2021. I'm Mark Reynolds. I'm a graduate engineer at FairHeat, and over the last sort of 6 to 12 months, we've been looking at the various use cases for rooftop solar PV and solar thermal to supplement urban heat networks in London. Recently outlined by the Committee on Climate Change's sixth carbon budget, heat networks are scheduled to provide 20% of UK heat by 2050, and that's up from 2% that we currently have provided by heat networks. Also stated by the CCC is that heat pumps are going to be instrumental in providing this increase in low carbon heat to heat networks. And one strategy for using heat pumps on heat networks is using a hybrid approach where heat pumps supply the majority of the heat and remaining peak load percentages are supplied by a gas boiler. This reduces the carbon emissions and avoids a high upfront capital costs required for a heat pump, which would supply 100% of the annual load. So this strategy will be a really useful way of integrating heat pumps into low carbon heat networks. And given that we're already seeing PV and solar thermal become useful for supplementing heat and electricity on a large scale, both in the UK and further afield in Europe, we wanted to investigate how that translates to the urban environment where roof space is minimal, but to see if there are any opportunities to use either of these technologies to further reduce the carbon emissions of a specific scheme. So that can all be boiled down really into these three separate research questions. The first question being, is it beneficial to supplement your heat pump electricity with PV, or is it more beneficial to supplement the heat demand of the network with solar thermal? The second question off the back of that is then, if you ignore solar, can you achieve the same carbon or cost reductions by just optimizing the heat pump and boiler heat fractions and sizes? And off the back of that, if the answer to that question is yes, and it is more beneficial to optimize your heat pump size, what is the optimum heat pump size considering carbon offsetting costs from a CapEx perspective? And so to answer these questions, we've built a techno-economic model taking into account the annual loads and generation profiles of different technologies and different size schemes to answer the above questions. And all of that will be pitted against a base case of hybrid air source heat pumps and gas boilers providing the peak load, where the air source heat pump is sized to provide 80% of the annual heat fraction. So if we look at how this scheme is laid out, we have a fourth generation two-pipe heat network, which is serving HIUs or heat interface units in each dwelling, which feed domestic hot water and space heating to underfloor heating systems. We've assumed a fourth generation heat network at 60 degrees to ensure that there's no boosting of temperature required within the dwellings. And then the central energy centre, which contains the heat pumps, boilers and the storage, can provide the total load to the network. PV and solar thermal will be installed on the rooftops, as you can see from the diagram, and CIBSE weather data has been used to model these outputs and to model the heat pump outputs using the ambient temperature data set. We've looked at 5 different representative schemes in London, from 100 to 1,000 dwellings, and these are either operational or in design. So the numbers of dwellings, blocks, and rooftop areas are all from building data which provide realistic modelling scenarios. To size the demand profiles for each scheme, we first looked at the annual dwelling demands and split those into space heating and domestic hot water. And these loads that you can see have been averaged from design calculations over each flat type to give a single annual heat load for each flat. These loads can then be diversified using diversity profiles, one for domestic hot water and one for space heating, and the constant annual losses from the standing HIU losses and the network heat losses can be added in to get the total hourly demand profile. If we move on to the diversity profiles, if we look at domestic hot water, this data was generated from 337 different dwellings taken between June the 1st and July the 31st in 2019 and 2020 to give us our domestic hot water usage only, where there was minimal space heating usage. The heat losses of the network were assumed to be the minimum loads experienced between 3 and 5 a.m. And those were then negated from the demands, and that gave us our pure domestic hot water hourly load profiles in both 2019 and 2020. And if we look first of all at the weekday profile, we can see that there's a significant drop in the morning peak load for domestic hot water between 2019 and 2020. And we think that can primarily be attributed to greater working from home and greater flexibility to use that demand throughout the day. And if you see later in the day, all of the profile from 2020 is more evenly spread throughout the day. And if we look at the weekend profiles, there's much less of a difference between the two, but the peak shifting towards later in the day is still exists on the Sunday and Saturday profiles, as you can see there. But it's a minimal effect, which won't have too much effect on the loads experienced in the model. And if we finally look at weekly profiles, we can see that again, there's not a huge difference between 2019 and 2020 per day of the week, with the biggest difference being a 1% difference on Friday, presumably due to, again, less flexibility to leave the home. If we then look at space heating as well, the degree days were used between the ambient temperature from the weather data and the heating temperature to generate estimated diversity factors for each hour of the model. The resulting profile was then compared to annual operational data, which shows that the combined hourly load profiles match very closely together. And we can see that from the load duration curve at the bottom there, where the only minor differences are that the real profile has slightly less time spent at peak load than theoretical, and slightly more time spent at low to medium loads. But generally, these are small differences which won't affect the modelling. If we then add all of these together, we can find our hourly demand profile for 350 dwellings. This is what this graph shows, which is the domestic hot water profile in grey, the space heating profile in orange, and adding those all up together gives you the total heat demand in red, which is what we're going to try and match with our generation profiles. And for those generation profiles, we're using heat pumps and boilers, again, sized at 80% heat fraction for all scheme sizes, other than where the heat pump heat fraction is changed. And thermal stores have been used on in each energy centre, and they've been based. The sizing has been based on the actual available space in those schemes, in those energy centres on those schemes. For PV and solar thermal, these availabilities have been calculated again using the City weather data for London, and the technologies used have been monocrystalline and evacuated tube solar thermal. All arrays have been modelled the same in facing due south of 30-degree tilt angles and same panel spacing and row spacing. Decision trees have been used in the model to help it determine what type of generation will be used to meet the demand for each hour. For heat, solar thermal is prioritised when it's available, and this incoming heat can be used to feed the network or the thermal store or both. And any demand that can't be met by discharging the thermal store or coming directly from the solar thermal will then pass to the heat pump and boiler decision tree, which is the second one on the slide. The heat pump and filling or discharging of its thermal store are then prioritised over the boiler to ensure that the boiler is used only as a last resort and only when instantaneous peak loads can't be supplied by other technologies. For electricity, the PV electricity supplements the heat pump and the other ancillary loads in the energy centre, and any surplus PV is exported to the grid, and then the shortfalls mean that electricity is imported from the grid, but no battery technology has been allowed for. For capital and operating costs, we've used linear cost factors, and the capital costs include the installed equipment costs and the carbon offset payment. And the operating costs include the electricity and gas tariffs, so energy costs, and the maintenance costs for each of the different types of technology. To determine the benefits of each different case, we've looked at 4 different KPIs to measure on each scheme and each different test. and those are total initial upfront capex, total carbon emissions of the scheme over 1 year, the total system lifetime cost over 30 years, and the delivered cost of heat to users. Looking at the results for a 350 unit scheme, where we've increased the size of the PV array versus the base case, we can see when we look at the capex, first of all, the capex increases as you increase the size of the PV, as expected. The carbon emissions decrease, which is also as expected. And if you look at the OPEX just above there, that decreases, which is due to the reduced electricity import from the grid, hence the lower carbon emissions. When we look at the total system cost and the delivered cost of heat, they both also decrease with increasing PV size on the roof. And that is because the reduction in annual OPEX is enough to offset the upfront CapEx to reduce the total system cost over 30 years. And the reduction in OPEX also reduces the delivered cost of heat to residents. One thing to note is that the PV utilisation rate was still 91% when the full roof of the 350 unit scheme was installed with PV. And that is because all of the electricity was able to be used by the heat pump and the heat pump electricity, or 91% of it was able to be used. And actually, when we pushed that further, we were able to see that actually there was no limit on any of the schemes because the total system cost reduces until a utilisation of 40% on all of the schemes, or around 40% on all of those schemes. And what that means is that there wasn't really a limit to the size of the PV array that could be installed where the capex wouldn't pay off. So the installed capex was always recouped by the reduction in total system cost over 30 years. Moving on to solar thermal, where we're doing the same things, comparing half roof and full roof solar thermal for a 350 unit scheme against the base case. And if we start again with capex, we can see that the capex increases with increased solar thermal size, slightly more than PV did. And if we then look at carbon emissions, we get a similar reduction, almost identical to that as PV, which is due to the combined reduction in electricity and gas. But you can see from the annual OPEX there that because the gas demand was reduced more than the electricity, there's actually only a very small reduction in OPEX. And because of that, the total system cost and the delivered cost of heat, the total system cost increases as you increase your PV size, as you increase your solar thermal size, so it doesn't pay off over 30 years. And the delivered cost of heat only reduces by less than PV. This is more evident when we start to look at the heat fractions. So this is the heat fractions for the different scenarios. And you can see that increasing the solar thermal size only generates an 8.6% heat fraction and takes more load away from the heat pump than the boiler. And neither gas nor electricity demand reduced significantly, which is hence why the OPEX reduction is small and not enough to overcome the increase in CapEx. If we look at the second question now, we've modelled increasing heat pump size with no solar thermal or PV from the base case. And if we look at what happens with CapEx, we can see that there is a reduction in upfront CapEx up to 95% heat fraction. And this is acting as a point of inflection due to the heavily reducing carbon emissions up to 95%, which we can see here. And due to this carbon reduction, the carbon offsetting costs required by the GLA in London are dramatically reducing and offsetting the increase in cost of the larger heat pump size needed to achieve that higher heat fraction. And after 95%, you can see that the carbon reductions diminish quite severely and the cost increases, but 95% is where the cost curve is at its minimum for CapEx. If we then look at the OPEX, we can see that the increase with heat pump size, which is due to the gas load being replaced by electricity, and this increase in OPEX also causes the delivered cost of heat and the total system cost to increase with heat pump size. But we can see the total cost increase is only small, up to 95% heat fraction. Finally, if we look at the effect of changing the demand profiles, we can see that heat pumps generally needed to be larger to achieve the same heat fraction under the 2019 profile than under the 2020 profile. And this is due to the more exaggerated weekday peaks that we saw in the DHW profile in 2019 that we saw earlier. Whilst this effect does become greater at higher heat fractions, the use of thermal storage in the model is able to help mitigate those peak loads somewhat. So moving on to the final conclusions. If we look at question 1, we can find that it's more beneficial to use PV to supplement electricity based on the metrics we looked at, and that is because the carbon reductions with either technology are fairly similar, but the CapEx for the PV is slightly smaller and also pays back up to 40% utilisation, and there wasn't really a limit to the size of the PV installation to be installed on the rooftop because most of that load was able to supply the heat pump. Moving on to question 2, is it possible to achieve the same savings by just optimizing the heat pump and boiler heat fraction? And the answer to that was also yes, where increasing the heat pump size gave the greatest carbon savings for the lowest upfront capex. However, as we've just seen, there is also a small increase in total system cost and delivered cost of heat, up to 95% heat fraction. But that is definitely something that is worth considering at planning and feasibility stages of a project due to the potential carbon reductions available from doing so. And finally, what is the optimum heat pump size when considering carbon offsetting costs? Well, as we've just said, that happens at 95% heat fraction, which is that point of inflection where both the GLA offsetting costs and the heat pump costs are minimized before the returns from increasing the heat pump size start to diminish and the capex increases again. So overall, where a heat pump hybrid system is being considered, it's important to maximize the heat pump heat fraction first in order to optimize carbon savings and cost. And once this is finalized, it's preferred to use PV over solar thermal to counterbalance these electricity costs that are introduced from increasing the heat pump size and further reduce the carbon emissions. So that pretty much concludes all the findings from the paper. Thank you very much for listening, and if there's any questions, please let me know. Thank you.